Cool. Thanks everyone for coming to this off cycle of PyHC Telecon. We won't have any more telecons for the rest of the year until the new year comes, which is crazy that is in less than a month. But here we are. The other big announcement I have is if you're going to be going to AGU, we have our poster session for PyHC on Wednesday the 13th, and that's going to be from 3:10 to 7:30 Pacific Standard. That's in Mountain Time, so it'll be 2:10 to 6:30 Pacific Time, the meeting time. So come join. Would love to see y'all there, and I'll make sure to put that link in the follow-up email for this telecon as well as in the Slack. So I think those are all the big announcements I have. So Baptiste, whenever you're ready, feel free to take it away.
Yes, so let's do it. So I'll share my screen here. Let me show this way. Oh, do you see the right screen?
We sure do.
Okay, good. So I will discuss today so developments that we've done in the last, let's say, years about Maser, which is a project dedicated to low-frequency radio astronomy data. So I will go very quickly in the first half on what we are talking about, and then go into the details of the Python package. So we are talking about heliophysics and mostly interactions between bodies and plasma flows, so solar wind and magnetospheres, or a moon in the Jovian magnetosphere, for instance. And at some time, depending on conditions, there are particles that are accelerated, and they, depending on the condition, they can emit radio waves in the low frequency range. So there is the well-known solar burst, the type 2 and type 3 bursts that are related to electron beams and interplanetary shocks, and also the auroral radio emission at Earth, Jupiter, Saturn, Uranus, Neptune. And so this is the scope of the phenomena that we are observing. They are very intense, much more intense than the thermal emission. So it's really a plasma instability, and they are sporadic. So it's usually difficult to predict. We can predict their statistical occurrence, but it's very difficult to predict when they actually occur. Just a closer view on the Jovian magnetosphere, which is impressive in the variety of radio emissions that we get there. So I put some Cassini-Arpeggios data on the right side, top right, and so you see the typical the data sets that we have. So there are dynamic spectra with time here in hours, and frequencies here from a few kilohertz to 16 megahertz. And so I just highlighted a series of the radio emissions classes that we see here, and they are coming from various places in the Jovian magnetosphere, which is a gigantic particle accelerator. And so those radio waves are emitted where there are unstable distribution function due to those electrons, and mostly electron beams. And they are related to the nice aurora that you can see at the bottom. So it's really those field lines that are bearing currents of electrons, beams of electrons, relativistic electrons that are emitting those radio waves. If you, just to show you the variability and why we need sometimes specific tooling, this is just 1 day of data during the Voyager flyby in 1979. You see those nice arc-shaped radio emissions that are typical from the Jupiter decametric emission. When you look close by to those regions, for instance, so it's not the same date, but here from a ground-based observatory for a few seconds of data, you see that there are plenty of stripes that are oblique, and each of those is a beam of electron that you observe over the poles of Jupiter. And if you have even a better sensitivity or resolution. This is from the Ukraine radio telescope, UTR-2, some years ago, and now it's not possible to observe because it's in a difficult situation. So those stripes here, individual stripes are electron beams, and the change in the slope are places, altitudes, where the particles are accelerated. So the change of slope is a change of speed, of kinetic energy. So it's really a very nice tool for remote diagnostic of particles in magnetized plasma. So this is why we are interested in this kind of phenomena and observation. So it's really sporadic and dynamic, and the scales varies from a few milliseconds to several hours, with variabilities that can be seasonal. So for instance, a few years or decades with giant planets. And now we are starting with very big telescopes to observe the same thing around active stars. This is an observation that was done, published this summer from the FAST radio telescope in China. And you see that all those stripes here are electrons beams that are falling onto the star. So you can observe individual beams also there from far away. So quickly, and then I go to the details, the technical details. What we are really observing are unstable energetic particles in magnetized plasma. Not always, but most of it. And so the radio sources could be plasma waves, cyclotrons, synchrotrons, or electrostatic discharges. So basically the lightnings in atmospheres. Those are non-thermal emission, usually very much polarized, or fully polarized, with a very wide time range of time scales, So we have developed, since a few years, a toolbox called Maser, which is aiming to be a science-ready toolbox for open science, for low-frequency radio astronomy. And the few key points that we want to highlight are being able to publish data, discover data, sharing the data, displaying data, and modeling data. So I just put a few examples of screenshots. So from left to right, this is data that is displayed through autoplot with a DAS2 server on the server side. Here it's machine learning of automated results of automated Jupiter decametric emission feature detection. And on the right-hand side, it's an interface of the run on demand for modeling. So here I put what Maser means. It's measurement, analysis, simulation of emission in the radio range. It's and the data product types that we have, as I said, are spectrograms, so dynamic spectra. So like the one here at the bottom with, so it's Cassini observations of flux density for 24 hours from 3 kilohertz to maybe I think it was 1200 kilohertz. And so you see various types of events. So there could be also waveforms that are observed, which, well, you know what waveforms are. So it's a high resolution time series, usually a short snapshot when you are in space. And then events that can be a burst of here Saturn kilometric radiation, for instance, could be this kind of noise, increased noise, which is in this case dust impact on the spacecraft. And well, a waveform is also an event, and so we in Maser we are trying to help providers and researchers to publish and use and reuse all those kinds of products. The landscape, in order to try to do things for technologies in interoperability, there is the astronomy standards, which provides us with interoperability-driven tools for schemas, protocols, vocabularies. There is the Planetary Data Alliance, IPDA, which is archive-driven, so it's more about so Planetary Data System, the NASA PDS, not using it so much as of now, but we have plans for doing so. And there's ID with it's really the driver to me is more of on the reuse of the data with tools, protocols, metadata and data formats. And also, well, here I included, I should have stated it in written, but I include Python heliophysics community in this community. And then for data publication, there is DataCite for the referencing and citation. So we have done a study on the users' needs when we started. So clearly there was a need for discovering data sets. They were distributed in various data centers, various teams who were proposing websites to share those data sets, usually in different formats. Sometimes they are very big. So for ground-based observations, modern radio telescopes, so it's difficult to transfer them before you are sure that you want to work with them. So there is a need for online access, mostly for pre-visualization, but it could be for just working on it. And also Python library for working with the data. And then there is the annotation and sharing of events or features catalogs. And then in the second step, we also identified that we needed to run models with a run on demand and hosting data sets. So we found in those ecosystems standards that were there already, or we invented just one. The time frequency catalog is something that we invented because there was a need here, and measure data that we developed for, and this is what we are going to focus on here. So here, this is a slide that I usually don't show because it's a bit busy. But here I think it's important to understand what is the architecture of our system. So the center are the data files. So we have data files that could be collections of files of a given instrument, given data level, and so in FITS, CDF, or whatever format, associated with quick looks, browse products. And so then around this, so we share them directly through a web server interface. So just a listing in a web server, that's one way. And we have also a metadata table based on the Vespa EPN core metadata, which contains the coverage of each data file in many dimensions. And then we share that using the TAP interface, Table Access Protocol from the IVOA. And this is the data discovery part. So we are integrated into the Vespa framework, and EPN TAP, so EPN Core plus TAP is really, for solar system, a way of having a homogeneous search interface. So you have to have a TAP client at this point. It's possible to do it in Python with a PyVO, for instance. And then you can search globally on all Vespa providers for data sets for a given query, like Jupiter, decametric range, and a given date, for instance. And then, so here, this is our discovery interface. So this is, and for that, so we use all those pieces of the architecture because Vespa is just a metadata table that points to a URL. And so we need this web interface to share the data. And then on the other hand, we have the remote access using DAS2. And this is also using the files, the metadata, the coverage metadata, and the tab server, because to transform the query into a list of files. So the query is a data set and in the time interval. So all this, so when a query arrives on our server, it's using this metadata table to find the files, and then the measure data is used to stream the data. So it's really a consistent ecosystem that we have built for our data services. So now coming to the measure data Python library. So it is, if you want to have a look on the code and everything, this is the URL here. You will get, of course, the slides at the end. The idea is to have a simple interface hiding all the details of the file formats, the various file formats that are there. We have included many datasets. I will come back to that. Yeah, on the baseline for CDF, we use PyCDF. We use a lot of AstroPy for times, units, and fits access. And we also use Xarray to have a common interface on all the data sets. And we are interested in being more integrated into Python heliophysics community. So this is why I'm talking here. So here you see yeah, a few examples. I will come back to that, and I can do a demo just after that with some quick start notebook and a list of data sets that we are covering now. So the initial idea was that there were many file formats. When it's easy, it's common either CDF or FITS, which are known formats, but there were also many older or maybe more recent ground-based data sets that are not using FITS and CDF. And so sometimes it's just binary or ASCII custom format. Sometimes it's other formats that are not from the heliophysics community. So the idea was to have a common interface. So basically you load from maser.data, import data, and you just load the file, the data this way from the file name. And the library finds out how to load the data. So the data set should be configured into maser data at first, but then the idea is that you don't have to think too much. Once the data is there, you always use it the same way, whatever the data set. So currently we are working with only local files. So having remote access to files is something that we want to have, but it's not done yet. So we can access and iterators on sweeps or records, depending on the type. So if we have time series, data.times gives you an AstroPy time object with all the times of each record. And data.records gives you a generator, and you can loop on your iterate on your data, record by record. The same thing can be done for dynamic spectra with times and frequencies, which are two attributes, properties that provides this information. And then you have two generators, sweeps, if you want to have a generator on a sweep per sweep basis. But you can also have a record basis iterator, which goes to each step of the sweep and then go to the next sweep and go each step of the sweep. So that can be also useful in some cases. So this make a homogeneous interface on all the data sets. And this is really the low level, I would say, interface. There is even a lower level. If you just try to get data.file, you have access to the native format interface. So if you have a CDF file, this will provide you with a space PyCDF object. If it's a binary file, you will have a binary IO buffer. Or if it's a FITS file, you will get this AstroPy HDU list object. So that's if you know that what you're dealing with and you already know how to use this data, you can go directly to the native format interface. And then if you want to have something that is more generic, we have this Xarray method. And so then you just load it as a data set with the metadata, dimensions, coordinates, and variables that are configured right away. Maybe one thing, yeah, internally, we are not storing the data into Xarray because it really depends on the way the data is stored on disk. So we keep, we only compute the Xarray interface when it is asked by the user. We have other interfaces for plotting, for instance. So we have a quick look method that we use, for instance, to build the quick looks, the browse products in our collections. And there's another subpackage, maser.plot, which allows to do a little bit more advanced plotting. I will not comment too much on this one in this presentation, but it's still very basic, and we plan to work in it a little bit more. And then there are other access or interface. For instance, to build the Vespa catalogs, we have a method that's providing a dictionary with all the EPN core keywords for that for the file that you're working with. And so this is used in our VirtualOps service server to create the tables, actually. So we provide the ingester in the VO server with the list of files, and it's calling, it's using maser data with this EPN core method to get the metadata and fill the table. We also have, we already have a DAS2 interface, but we plan to implement a maser DAS2 sub-package at the moment. And well, this is what we do, but it's not yet completely implemented in all data sets. But basically, on a DAS2 query, you receive a query, the server receives a query for a data set and a variables and a time interval. And so we use our internal Vespa registry to find which files should be loaded on the server for this query. And then we use the sweeps generator, the iterator, to go through the files and serve the stream data in DAS2. We also plan to have a resource descriptor in Space, but it's not done yet. So we are trying to develop in a nice way. So we are developing the package using Poetry, Precommit, and Black. We use PyTest for the tests. We try to do as many unit tests, the unit test along with the modules that we develop. So here I just tested the PyTest just before the presentation. So it takes some time to do all the tests because we have a lot of files to read, so we should probably improve on the size of the file to have test files that are smaller than actual files. Here we only have, we really take a real life example of files from the collections. So this is something that we can improve. Some are failing because I didn't have the files. I have to ask for them. I didn't load the file at the right time. But we have a quite good coverage report, quite good coverage using the tests, and so this is something that we want to improve. And our code repository is using our local GitLab repository at the Paris Astronomical Data Center. And when we push to the server, there is some continuous integration, linting, testing, and publishing, well, depending on if we, on the type of where we push. If it's pushing on the main branch, for instance, it's also pushing to PIP, publishing in PIP, and pages for the documentation. We have also a small internal table to review our development, the development status of our features, which is quite useful. So it's so you can see here the variety of things. And the other thing that I didn't mention, for instance, mock and TFCAT, we also plan to have this kind of interface, but I will not comment here. It's for next time. Currently, this is the list of supported data sets. So we have ground-based observations. There's the eCallisto framework. So we can read the eCallisto fits data. Nancy data, routine, so the decameter array, the routine, new routine, and Mephisto instruments. And for the Nenufar instrument, we also have the low resolution, the beam statistics data. And for space-based data sets, so it's from various data centers. From CDPP in Toulouse, we have the interball, we can read interball data, stereo waves level 2, wind waves level 2, level 3. From our local repository, we have, so it's still private data, but it's working. The Baby Colombo data from our instrument. The Cassini RPWS HFR from not all data levels, but we have some of it, and the rest is coming. Modeling, Express is so exoplanetary and planetary radio emission simulator. And so we have for various places, Earth and spacecraft, the prediction of where radio burst, Io Jupiter radio burst could occur. Juno waves. So we have a data set that we are producing with level 3. If I say calibrated, some people in Iowa will be angry, but it's somewhat calibrated. Well, it's sort of a calibration. And zero waves, level 2, level 3. Wind waves, we have 2 types of level 3 data, direction finding and AKR. So it's we had a postdoc working on that, extracting oral kilometric radiation samples from wind waves, and solar orbiter RPW. And from PDS, at the moment, we have Voyager PRA, the planetary radio astronomy experiment from so low band and high band data sets. And from Cassini, we support the low rate, and I'm not sure we support actually the wide band, but it used to be, but probably it has to be fixed. I'm not sure it works now. And from the Planetary Science Archive of ESA, we also support the Mars Express Marsis data sets for passive observations, where we can see radio burst actually. So this is why we included this there. Next, so we plan to have more data sets supporting our projects, Solar Orbiter, Juno, Bepi-Colombo, and JUICE. So that the 4 that we are working on now. We want to add support also for astrophysics data sets, mostly from ground observatories, because there are more and more people working, needing to have the same kind of capabilities as those that we have developed for MASER, for solar system radio emissions, for pulsars, active stars, exoplanets, fast radio bursts. So I didn't list everything. Because yeah, that seems to be useful for them also. And we also will use MASER data in the ground segment of our radio data sets produced by JUICE and Bepi-Colombo. So we plan to develop the DAS2 sub-package soon to try to have a better integration. At the moment, it's bits and pieces that are a little bit independent, and we want to have a common way of doing it. Try to have the capability also to load remote files from a URL, so it includes a way, it should include a way of caching the data somewhere, and also from data sets. So having a data set ID and then an interval, and find the files and load the files and display them. We also want to simplify a bit the environment, the development environment. Poetry is nice, but it's a bit complex, and when it doesn't work or it doesn't, well, it's sometimes a headache to fix it. So we are thinking of removing poetry, but not removing what we try to have as to try to enforce quality on the code. And also the discussion point, which is here, is how to be integrated into Python geophysics. Are there ways of, would there be benefits to have tighter links with SunPy, for instance? So those are open questions, and this is why I propose to discuss here. So I'm finished with the presentation. I have some notebooks where I can just demo quickly, but maybe we can go to the questions and we will see what happens.
Thanks, Baptiste. It looks like you had one question in the chat from Rebecca.
Okay, I didn't see that chat. Now I have to open the chat. Yes, I have to open it. The X-ray interface work for all of the, yes, we have implemented the X-ray interface on top of all. This is for all the data sets.
Cool. Any other questions?
Yeah, I've got a quick question. Baptiste, what do you envision for the interaction with SunPy going forward?
I don't know. So the idea could be, I don't know, that I didn't have a close look on how we could either merge or interact. So I'm not sure we are doing the things exactly the way you did, but we started we had a look at the beginning with our former developer on how SunPy is doing to load data. So we tried to do something similar. It's probably not exactly the same. So it could be, I don't know exactly. One thing that could be nice is that if somebody's trying to load a file that is available with a Maser data reader, it can be loaded into SunPy without. But yeah, I don't know. This is really open.
Okay. Yeah, I don't know. I don't know either. So there's a lot of SunPy development is kind of closely tied to FITS files and the information carried around in FITS files. So I don't know if how much overlap there would be with the types of metadata that.
Yeah. But the thing is, for instance, when we started, we first tried to see if we could just use SunPy. And for instance, there was the fact that basically we are doing dynamic spectra, and all the WCS information on the pointing and the field of view and the transformation coordinate, the spatial coordinates is just useless for us. So it was a big overhead at the beginning when we tried to do. So we switched a little bit with a more simple, well, at least a way that where we didn't have to manage coordinates because we didn't need coordinates, or at least the spatial coordinates. So that could be one thing. If indeed, that is a bit different.
Now there is a radio spectra package.
Yes, there is from Dublin, and from Shane Maloney, I think he's. So I discussed a lot with him, and actually we have plans to join forces. So that would be probably good, because at the moment he's only supporting, I think, 2 data sets. So it would be probably good that we try to at the moment, and I think it's 2 data sets that we support too. And it was developed in the frame of Solar Orbiter, if I remember well, or Parker Solar Probe, where there was this need well, they had this need, and at the time where they developed that, Maser data was not ready for being used. So this is why they did it. But yeah, we had a lot of discussion. It's just that Shane and I are very busy, and so finding the time to be at the same place for long enough to do that is yeah. But yeah, there's the will to do it.
Yeah, and looks like there might be some overlap, at least with the Python with the SunPy ecosystem. That's good.
Yeah. So.
All right, thank you.
Any other questions for Baptiste?
I have one that's off topic. Okay, if no one else is, okay. So I've been poking around on different things for so many different topics. But one thing that I saw, and your mention of the run on request thing jogged it, is this idea group, the IHDA group about scientific computing jobs. And I was wondering if you could take a quick moment and describe what's going on with that.
You mean on the run on demand on the Maser side, or on on the ID working group?
I don't understand how they're different. So whatever,
So,
whatever
so
helps.
yes, I don't have so much details to show, but on Maser, we have used a solution that is developed in the frame of the IVOA, so the Virtual Observatory for Astronomy, called UWS, which stands for Universal Worker Service. And so it's basically a layer that is added on top of a job manager on a computing cluster. For those who know, it can be interfaced on Slurm, for instance, which is one of the main job management system on clusters. And so it's then there is an API that is standard on all the VO servers, and you can ask for a job, computing with some description language, and then you retrieve the results. And so this is something that in the working group of ID, it has been mentioned, but it's not so much active. So I don't know exactly what's the... I'm not sure if there was any development recently on that working group. This is something that we should probably revive. Probably need people interested to it and
Right.
trying.
Two
So,
questions on that.
yeah.
First, when CCMC uses the phrase running models on demand, what they
Mm.
really mean is people put a request in, staff goes to set up and run the model for them, and then there's like
Yes.
people in the loop. And it doesn't sound like the same thing that you're describing.
No, what we do is really run on demand. So what we have to, the way it works, you have to, on the server side, so as a provider, you implement software code, a modeling code, with an interface which can be called. So usually it's a script that you can write with parameters, and you submit the scripts through that interface. So there is no one that is pushing the button on the server side. You as a user, you can submit a job, and the job is running, and you get the results. So it means, so we have two modes. We have the mode where you can submit a job as a guest user, but it's a limited job, so limited in memory, limited in time. But then if you register, you can have longer runs and larger virtual machines or larger, more memory. But here the idea is really to have codes that are implemented behind this run-on-demand system, and people can send a query through a script, run the code, and get the result. And this is what we did, for instance. So for this Express modeling code, which can model the occurrence or the statistical occurrence of Jovian radio emission for the location of a given location of an observer, and the JUICE ground segment team at ESA, they are querying our server to prepare the segmentation of the orbits. So when is it interesting to observe Jupiter or not, depending on if we see the radio emissions or not. And so they query our server, and the server is computing, sending back the result to Madrid, to Isaac. And that's working behind the scene. We don't even we don't have to know that it's working. So
That's
it's
cool.
different way than CCMC, where yeah, as I understand, you have to have someone running it for you.
Yeah, that sounds more like their instant run service.
Yeah.
Yeah. Okay. So last comment is at the Gigantic Symposium about a month ago, there was a lot of cross-disciplinary people there, and one of the things they mentioned that's starting to tick up, if that's the right phrase, is that there's starting to be work on how to use supercomputers where you submit job requests from the web. Are you nodding because that's a you already know about this, and I'm just
No,
preaching
no,
to
no,
the
no. I'm
choir.
nodding because yes, this is something that is rising, but no, I don't know about that discussion that you're
Okay,
mentioning.
I text somebody to contact this idea group that's supposed to work on the scientific job stuff, and I think you're
Mhm.
on it. Is that correct?
Yes.
Okay, so maybe I email you and the person to get that
Yeah,
connected.
yeah. But it would be good if there are some other people in the working group that are available, because I can't do everything.
Yeah, yeah.
But yes, for sure, I can redirect to things. I don't know exactly. I've not followed recently in the astronomy virtual observatory how far they go with the integration of UWS for supercomputing. It's mostly for small jobs. For instance, it is used internally for VO requests that are done asynchronously. So if you send a TAP query, so table access protocol query that takes too long to be to get a response before the web server times out, then it goes to an asynchronous query, and it's using UWS as an interface for this asynchronous job. So I don't know any use, if there is any use for supercomputing, but yeah, I don't know. To me, the main problem of supercomputing is the access to the servers and the facilities, because usually those are yes, cost money to run them. So you can't really well, it's difficult to open up to anyone. And
Yep,
usually
yep.
there are places where, yeah, some people cannot connect for probably good reasons or not, but so yeah, it's not that simple.
They're working on opening it up for government-funded supercomputers.
Okay.
Okay,
Mm-mm.
I think we can carry this offline now.
Yeah, sure.
Thanks.
And we can discuss next week probably if you are going to San Francisco.
My sunflower backpack.
Cool. Any further questions for Baptiste?
Well, then, if not, thank you very much for inviting. So yeah, I don't know how we can try to follow up on. So maybe what would be the steps for being part of Python Heliophysics? First step would be to be listed on the list of packages, for instance.
Yeah, I would start by doing a pull request via the instructions that you'll find on the projects page. And then myself, mostly Sean, we'll review it and make it good with our standards, and then we'll publish it. And if you have any other significant updates since then, in the meantime, you can always come back on a telecon and give some quick presentation on it.
Okay. So yeah, okay. We'll have a look. I don't know if I can have a look with that by next week, because time is short. But I'll try with Luca. So he's online. He's one of the main developer now with me. He started a few months ago, and he's done a lot of things. So it's good.
Luca.
Yeah. And so I asked him to register to the PyHC mailing list so that he receives the announcements.
Oh, well.
And yep, so
Cool. All right. Sean, you had missed the beginning. Did you have any quick updates you wanted to give while we're all here?
Yeah, other than the continued effort happening on the pull request for FEP1, I can't really think of much to announce, but I'll take the opportunity to encourage people again that is now out of draft and open for actual review, and we are encouraging input on that.
Yeah. Awesome. Well, I don't have any other big ticket items, so thanks again, Baptiste, for coming and telling us about all the work y'all have been doing. And I'll see you all again officially in the new year. I forget, it's probably the second week of January that we have our first telecon to give everyone time to come back.
Okay.
Thank
And so if
you.
you want to discuss with me, I will be at the NASA PDS booth mostly the full week. So pass
Sweet.
by.
Okay.
Cool.
Yeah. Bye-bye.
Bye, y'all.